Hello and welcome to this second online video lecture for your second semester of chemistry. This lecture is about what's known in chemistry as the gas laws. And the gas laws are mathematical relationships between two of the three properties you see on the screen here, volume, temperature, and pressure, in terms of gases. These three properties are mathematically related to each other in the behavior of gases because of the fact that they're made of particles that are constantly moving. So before we get started with the new stuff, let's just do a quick review about these three properties right here, what they are. Volume is the amount of space that something takes up. Temperature is the kinetic energy of the particles that the matter has, and for most of the work that we do with the gas laws, you have to use a unit called Kelvin. And Kelvin is based on absolute zero, which is where the particles of matter would have zero kinetic energy, which theoretically isn't possible to attain in our universe, but we base this temperature scale on that. So if I wanted to take a Celsius temperature and convert it into a Kelvin one, I would have to add 273. So that means that freezing, it's 0 degrees Celsius, is 273 Kelvin, and there's no degree symbol with that. And then the last one is kind of a compound unit, but it's the force that's exerted by matter over a surface area. So pressure is what keeps like a balloon inflated. It's the force that the molecules of the gas exert as they hit the interior surface of the balloon. And that's what keeps it blown up. That's called pressure. So pressure is basically a force, and the most commonly used measurement unit on that measurement is going to be atmospheres, which is ATM. Because the air around you also has pressure. It exerts pressure on you, and at sea level the amount of pressure that the air of the atmosphere is exerting on you is 1 atmosphere. That's the unit that they use. So now that we just kind of have a little quick review out of the way with that stuff, let's actually get into what you need to know here. By the end of this lecture, you should be able to take any one of these three properties, and you should be able to kind of know what they are. You should also be able to explain how any two of these three are related to each other. So I'm just going to take the pairs in order, and we'll just start with volume and temperature. And temperature. A lot of these you already instinctively know because you've kind of experienced them your whole life. So if you think about, say, like a balloon. If you have a balloon, I think most people have experienced this in their lifetime. If you take a balloon and you inflate it in your house, you know, where the temperature of the air that you're inflating it with is, say, I don't know, we'll say 23 degrees Celsius. So what would that be? That would be 296 Kelvin. And then you take it outside on a cold winter day in Michigan, and we'll just say it's freezing outside, so it's 0 degrees Celsius, which is, of course, 273 Kelvin. You know what happens to that balloon as the temperature of the air inside of the balloon drops, and that is that the balloon shrinks. So it goes from being fully inflated to being kind of a pathetically small, shriveled up little balloon. And so basically what's happening here is the relationship between volume and temperature. So as the temperature of the air inside of the balloon decreases, the volume of the balloon also decreases. So this is a direct relationship, and these two, it's also a linear relationship. So as the temperature of the gas inside of the balloon decreases, the volume of the gas inside of the balloon decreases. And we see this in all gases. If the temperature is low, the volume is low. And the opposite of that is if the temperature is high, then the volume is high. So it's a direct relationship. If the temperature is low, the volume is low. If the temperature is high, the volume is high. And so if we were to graph that, which I'm going to do right here, let's make a little line graph of this direct linear relationship. If I had, let's say I had temperature on the x-axis, and I have volume on the y-axis, So if the temperature is high, the volume is high. So what would that be? Well, the temperature high is over here. If the volume's high, it's over here. So that means if they're both high, you'd have a point somewhere over here. And then temperature low, volume low. If the temperature is low, that would be a point, say, over here. And if the volume is low, that would be down here. So we're looking at a point like right here. And so what you get then is you get a line that goes like this. It's a direct linear relationship. And it's direct, so as this variable increases, this variable increases. So you get an upward slanting line. So that's what you have to remember. You have to remember that if the temperature of a gas goes up, the volume also goes up. If the temperature of a gas goes down, the volume also goes down. Or if the temperature of a gas is high, the volume's high. And if the temperature is low, the volume's low. It's not always a causal relationship. Sometimes it's just how it is. So that's temperature, volume, temperature. And for those of you who are even remotely curious about such things, this law actually has a name. It's named after a man who discovered it. And the man who discovered it, his last name was Charles. So this is called Charles's law. And I know that looks like it's spelled incorrectly, but that's actually how you do it because his last name was Charles. So high temperature, high volume, low temperature, low volume. That's the relationship between those two. So now we did temperature and volume. Let's do temperature and pressure. So this is the temperature pressure relationship now. So the one that I like to use to explain this one is, let's say you have a can. It's a sealed aluminum can, and inside of the can there's a gas. If you throw that can into a fire, like let's say you've got a big bonfire going here, right? You got a big old bonfire going, and you throw the can into that. I think a lot of you know that you shouldn't actually do that. It's very, very dangerous because, again, eventually what happens is if you throw a sealed aluminum can into a bonfire, it will explode. And the reason for that is the relationship between these two. And that is that if temperature is high, then pressure is high. So again, we have a direct relationship. Temperature is high, pressure is high. If temperature goes up, pressure goes up, and that's what causes the can to explode. And so if we wanted to graph that, if we put temperature down here and on the x-axis and pressure over here on the y-axis, again, it's a direct linear relationship, so you get an upward slanting line. The reverse of that, of course, would be that if temperature is low, then pressure is low. So that's the temperature-pressure relationship, and that's why it's dangerous to throw sealed containers into high temperature situations, because you can cause dangerously high pressures. Okay, and that leads us, oh, by the way, that, if you're curious, the name of that gas law is after the Frenchman that discovered it, and that Frenchman's name was Gay-Lussac. So it's G-A-Y hyphen L-U-S-S-A-C. So it's Gay-Lussac's law, if you want to learn more about that. Okay, and so that brings us to our third law. And this one is the volume pressure relationship. So for this one, I like to use a syringe with a cap on the end of it. Syringes are marked with volumes, and as you press the plunger down on a syringe, you are decreasing the volume inside of the syringe. That's how syringes work. So a syringe like this would have a large volume, And then if you took the same syringe and you pressed the plunger down here like this, then it would have a relatively low volume. And so I think most of you know what happens to the pressure inside of a syringe when you do something like this. If your volume is high, then your pressure is low. So this is an opposite situation. And then if your volume is low, your pressure is high. So this is an inverse relationship. An inverse relationship. And this one isn't linear. So I'll draw a little graph of this here. Basically, if we've got pressure down here on the x-axis, and we have volume over here on the y-axis, if you graphed the two of those, it's not a linear relationship because it's really hard to get either of those to be 0. So basically what you get is you kind of get a curve like that. But the relationship stands. You know, when the volume is high, the pressure is low. But when the volume is low, let me get another color real quick. Volume is low, right? The pressure is high. They're opposites in this case. It's an inverse relationship. So those are the three gas laws, and those are the three relationships you need to know. You need to know that volume and pressure are inverse. So low pressure means high volume, and low volume means high pressure. You need to know that temperature and pressure are direct relationship, direct linear. So low temperature, low pressure, high temperature, high pressure. And you need to know that the volume temperature relationship is also directly linear. So low volume, low temperature, high volume, high temperature. So that's it for this online video lecture. If you have any questions, as always, feel free to ask in class, and thanks for watching.